Now that you guys have learned how to draw the orbital diagram for elements when given their electron configuration, one last concept that I need to introduce is the concept of paramagnetism and diamagnetism. Now, if an element is paramagnetic, what that means is that one or more of its electrons are unpaired. So when you draw the orbital diagram, the element has one or more unpaired electrons. And as a result of these unpaired electrons, those elements are going to be attracted to an external magnetic field. And so here are some examples of paramagnetic elements. As you can see from their orbital diagrams, for example, aluminum has one unpaired electron, silicon has 2, phosphorus has 3, and sulfur has 2. Now, if an element is diamagnetic, what that means is that all of its electrons are paired, and as a result, elements that are diamagnetic are not going to be attracted to an external magnetic field. And so examples of these, anything that has a full orbital. So for example, if the 2p orbital were filled, or if the d orbital were completely filled so it does not have any unpaired electrons. So that's paramagnetic and diamagnetic. It's a really nice laboratory technique. It can help us to identify an element based on whether we anticipate it being paramagnetic and diamagnetic based on its orbital diagram.
So as part of your summer assignment, you went over all the different periodic trends that we talked about during our first year of chemistry together. But I really quickly wanted to review some of these trends and then add on to it. So the first thing is talking about atomic radius. Radius in general is going to decrease in size. And the reason why it does that is because the number of protons increases. And protons, remember, are positively charged. And therefore, their charge is going to be increasing as you move across the periodic table because you have more and more positively charged particles. The way that we express that is that we say that the elements are going to have a larger effective nuclear charge, or the effective nuclear charge increases as you move across the periodic table. Okay? Now, as you move down the periodic table, atomic radius increases. And the reason why that happens, remember, as you move down the periodic table, your number of principal energy levels increases. So you start with the first principal energy level with hydrogen and helium, then the second period is going to be 2 principal energy levels, then 3, then 4. So keep in mind that the reason why the atom gets larger is simply because you have more and more principal energy levels. And now what I'm going to be talking about is ionic radiuses. So what happens, we've just compared the size of atomic radii, but what happens if we actually alter the number of electrons, right? If we add electrons or we take away electrons, how would that affect the size of an ion compared to its parent atom? So the atom that has not had electrons added or removed.
Well, if you have a cation, meaning a positively charged ion, the way you got that cation was by removing an electron. By removing an electron, you actually decrease the size, so cations are smaller than their parent ions, and that's because they have fewer electrons. Now, electrons are going to repel one another, so the fewer electrons you have, the fewer repulsions you have, and therefore it's going to be much more neat and tidy, and the electrons are going to be pulled towards the nucleus. Now, if you have an anion, anions are going to be larger than their parent atoms, and that's because you have more electrons and therefore you have more repulsions. If you look at the oxide ion, fluoride ion, sodium ion, the magnesium ion, and the aluminum ion that I've given you, it says that they're isoelectronic, meaning you have the same number of electrons. So it wants us to list these in order of increasing size. Well, aluminum has the most protons, therefore it has the largest effective nuclear charge. And since they all have the same number of electrons, aluminum is going to be the smallest, followed by magnesium, followed by sodium, followed by fluorine, which is much bigger, the fluoride ion, followed by oxide.
Another trend we talked about and we looked at over the summer was ionization energy trends. Okay, so keep in mind that in general, when you move down the periodic table, since the size of the atom gets larger, the ionization energy is going to decrease. And that's because as the atom is getting larger, the electron you're removing is going to be further from the nucleus. Now, as you move across the periodic table, the ionization energy is going to increase. And keep in mind that's because the atomic radius is decreasing, so the electron that you're trying to remove is going to be closer to the nucleus. Now, that's review. What's new is there are actually a couple of exceptions that you're expected to know. Now, they wouldn't expect you to remember these in the sense that you would have to be able to say this one has a higher ionization energy than this atom. But what they would expect you to be able to do is if they told you, hey, this atom has a higher ionization energy than this atom, why? Then you would need to be able to explain. So let's look at these two exceptions. The first exception. The first exception is between group 2 and group 3. So let's see that on the periodic table. So group 2, remember, is beryllium, magnesium, calcium, strontium, barium, and radon. Okay, and group 3 is going to be your boron, aluminum, gallium, etc. Okay, so let's talk about why there is an exception for ionization energy trends. So what we would expect is that based on the trend that we just talked about, boron should have a higher ionization energy than beryllium, aluminum should have a higher ionization energy than magnesium, etc. That's not what we see though. And so we need to figure out why. Now, keep in mind, when we are removing an electron from beryllium, we would be removing that 2s electron, right? So it's 2s2, we would be removing one of those electrons for it to become 2s1. Or if we were removing the magnesium electron, it would go from 3s2 to 3s1. So we're removing an electron from 3s. Same thing for calcium. Now for group 3, we would be removing it from the p sublevel. So for boron, for example, we would be removing a 2p electron. For aluminum, a 3p electron. For gallium, a 4p electron. So there's an exception here because boron actually has a lower ionization energy than beryllium. Aluminum has a lower ionization energy than magnesium, which we don't expect. And the reason why, as you can see, for example, boron versus beryllium, the electron being removed from boron is from the 2p sublevel, whereas the electron being removed from beryllium is from the 2s. Now, if you think about it, remember, as you increase sublevels, as you go from 1s, 2s, 2p, etc., you're moving further and further away from the nucleus. So 2p, if you're removing an electron from 2p, that is farther from the nucleus than 2s, which means it's going to be easier to remove because it's further from the nucleus, therefore it is not experiencing the same pull from the nucleus. Okay, so group 2 versus group 3. Group 3 actually has a lower ionization energy than group 2, which goes against what we had just talked about as far as trends are concerned. And that's because the electron that's being removed is being removed from a sublevel that is further from the nucleus. Okay, so that's the first exception. The second exception is group 5 versus group 6. So group 5 starts with nitrogen, so you've got nitrogen, phosphorus, astatine, antimony, etc. Group 6 is oxygen, sulfur, etc., etc. Now, we would expect, again, that oxygen would have a higher ionization energy than nitrogen, sulfur higher than phosphorus, because ionization energy in general increases as you move across the periodic table since you are increasing the effective nuclear charge. However, this one's a little weird. So if we compare the orbital diagrams for nitrogen versus oxygen, or for phosphorus versus sulfur, for example, the nitrogen and phosphorus and astatine would have the first orbital diagram that you see on top. So you'd have 3 electrons in 3 different orbitals. They would all have the same spin and they would not be paired. Okay, so it would be paramagnetic. Group 6 looks very similar, except you've got one additional electron, and so that additional electron, which I've circled in green, is paired with another electron. That's why it has the downward spin. So that actually does matter. Because electrons actually repel each other, group 6 elements have a lower ionization energy than group 5 because their electron that's being removed is paired And therefore, since electrons in the same orbital would repel each other, it's going to be easier to remove that electron, and therefore it's going to have a lower ionization energy. Okay? So group 6, just as a review, elements are going to have a lower ionization energy than group 5 because the electron that you're removing from group 6 is paired, while the electron that you're removing from group 5 is not paired. Okay? Now, that created the question in previous years of, well, hold on a second, what about group 6 and 7, right? So for group 6, you'd have one that would be paired. What about if you have two that are paired? At that point, it doesn't make a difference. The main point here is that for group 5, none of them are paired, and therefore you don't have electrons repelling each other to the same degree. Whereas for group 6, you've got that one electron that you're trying to remove that is paired, and therefore it's repelled, so it's going to be easier to remove it. Okay? So those are the two exceptions. Just to make you guys feel more comfortable, remember, I wouldn't say, hey, what is the difference in ionization energies between nitrogen and oxygen, and hope to catch you and have you make a mistake because it's an exception. Instead, they might state, hey, oxygen has a lower ionization energy than nitrogen, which goes against the periodic trend. Explain it. And then you would be expected to go back to these two exceptions and explain the reasoning.
The last concept we're going to go over is successive ionization energies. There isn't just one ionization energy. Instead, with each electron that you remove, there is an ionization energy that goes along with that. And as you would expect, if you look first and compare simply I1, which is the first ionization energy, and I2, there is an increase, and that should be expected because if you think about it, if you remove one electron, to remove another electron, you are getting rid of an electron, which means that the nucleus is going to be more effective at attracting more electrons. So it should increase with each ionization energy. What shouldn't happen, as you can see, is these sudden huge jumps in ionization energy. For sodium, it's between I1 and I2. For magnesium, between the second and the third ionization energy. We expect an increase. That makes sense as an atom becomes more and more and more positive. Okay, but why is there such a huge increase? And that's because if you look at the periodic table and consider the electron configuration of sodium, sodium is 1s2, 2s2, 2p6, 3s1. If you remove that first electron, that's in the outer shell of electrons, and therefore it's going to be easier to remove because it's farther away from the nucleus. It has a lower effective nuclear charge, and therefore it's very easy to remove that electron. Now, if I try, after I remove that first electron, if I go and try and remove a second electron, at that point I'm removing electrons from the inner shell of electrons, which experience more attraction to the nucleus, are closer to the nucleus, and therefore it's going to be a lot harder to do. And so if you notice from I1 to I2, there's a huge jump in ionization energies. Now, just to make sure we're clear on this, if you look at magnesium, notice the first ionization energy and the second ionization energy there's not a huge difference, there isn't a big leap. But then going from the second ionization energy to the third ionization energy, there is a big leap in ionization energies. And that's because in order to remove those first two electrons, those are from the outer shell. And therefore, they're not experiencing as much attraction. They're farther away from the nucleus. They're fine. But as soon as you start trying to remove electrons from the inner shell, the 2p, that's going to require quite a bit more energy, and in fact, almost 7 times as much energy as it was to remove that second electron. And so as a result, as you can see, ionization energies will increase as you remove the first, the second, the third, but then you're going to have big jumps as you start removing electrons from the inner shell of electrons.